So in question number 1, it is given that molality of dilute solution is doubled. If molality of the dilute solution is doubled, the value of molar depression constant will be. Okay, you know very well. Question number 1. Okay, molality of the solution is doubled. Right? What will happen to the molar depression constant? You know very well, molar depression constant Kf, right? Kf, right? How this is related to molality? Okay, listen students, this is very important. You know very well, delta Tf is equal to Kf into m, molality, right? Listen, if you vary molality, delta Tf will change. If you vary molality, delta Tf will change. If you increase molality 2 times, delta Tf will increase 2 times. But Kf value depends on your solvent. Okay, this is purely depends on solvent, right? So varying molality of the solution, right, does not affect the value of Kf, right? So Kf value is unchanged. Therefore the correct option for this question is C. Students, observe this carefully. As long as the solvent is same, Kf value does not change. Okay, is this clear, student? Any doubt here? For question number 1, the correct option is C. Delta Tf will change, not Kf. Kf is proportionality constant, and that constant depends on your solvent, right? See, you are increasing the molality of the solution, you are not changing the solvent, right? Therefore the Kf value remains same. Okay, now let me go to the second question. Go through the second question, students. Which of the following is dependent on temperature? Yeah, some concentration terms are given here, right? Which are all the concentration terms depends on temperature? You know very well, molarity. What is molarity? Number of moles of solute by volume of the solution in liter. Normality, number of moles of solute divided by volume of the solution. Number of equivalents, right? It's not number of moles, this is number of equivalents of solute. Let me write like this. Let me write instead of N2, I'll put number of equivalents. Number of equivalents, right? Number of equivalents of solute divided by volume of the solution in liter. That gives you normality. Similarly, percentage mass by volume, right? And percentage volume by volume. Okay, then yeah, these things, right? These are all concentration term that depends on volume. See, that depends on volume, right? And you know very well, volume depends on temperature. As temperature changes, volume will change. If volume changes, these concentration terms will change. So molarity, normality, percentage mass by volume, volume by volume, all these concentration terms are temperature dependent. Okay, so you just go through the question number 2 again. Which of the following is dependent on temperature? Option A is molarity, mole fraction, option C weight percentage, and molality. You know very well, these quantities, percentage mass by mass, see, both are mass, it does not depend on volume, right? And molality, what is molality? Number of moles of solute divided by mass of solvent in kilogram. No volume here, no volume. And mole fraction of solvent or solute is equal to number of moles of solvent divided by total number of moles, correct? Here also there is no volume. So in these terms, even parts per million, in these terms there is no volume term. In this concentration term there is no volume term. Okay, if there is no volume term, then these are all temperature independent. These are all temperature independent terms. Therefore, among the options, if you go through, option A alone is temperature dependent. So for question number 2, the correct option is option A. Right? Among the given 4 options, only the molarity depends on temperature. Okay. Then question number 3, the Van 't Hoff factor. Students, go through the question. The Van 't Hoff factor for a dilute aqueous solution of strong electrolyte barium hydroxide is. Okay, you know very well the formula of barium hydroxide is BaOH twice, and it is given clearly it is a strong electrolyte. Strong electrolyte will undergo complete ionization, you know that. Okay, therefore alpha equal to 1. It undergoes complete dissociation, so alpha is equal to 1 usually for strong electrolyte. Therefore, Van 't Hoff factor I is equal to number of ions obtained from one molecule. Van 't Hoff factor I is equal to number of ions. See, when barium hydroxide ionizes, when one molecule of barium hydroxide ionizes, I'll get one barium ion and 2 hydroxide ions. I'll get 2 hydroxide ions. So here 1, here 2. So number of ions produced from one molecule is 3. Number of ions produced from one molecule is 3. Therefore, Van 't Hoff factor is 3 for this case. Van 't Hoff factor equal to 3 for barium hydroxide. Students, is this clear? Any doubt in this? Yeah. So for question number 3, the correct option is D. Option D. Correct option is D. Take note. You have to see the electrolyte carefully, whether this electrolyte is strong or weak, whether it undergoes dissociation or association, right? Yeah. If it undergoes association, they will mention. They'll mention whether it will undergo association or not. Okay. Yeah. Now, let me go to the next question. See question number 4. Which of the following is incorrect for ideal solution? Delta H mixing is given, delta U mixing is given, delta P, delta G mixing, right? First, I'll give you the ideal solutions, some of the results of ideal solution. For ideal solution, students, remember, for ideal solution, delta V mixing should be 0. Delta H mixing should also be 0. Delta U mixing, since delta H mixing is 0, your solution is a liquid solution. Okay, in the case of liquid solution, delta H and delta U are almost equal. Therefore, delta U mixing is also 0. Delta H means change in enthalpy. Delta U means change in internal energy. Okay. For solid and liquid, delta H and delta U are almost equal. Therefore, that values are 0. Okay. Then third one. This is the third one. Then fourth one. Delta S mixing. You all know that. Delta X mixing should be positive. And delta G mixing should be negative. Should be negative. And I have also told you for ideal solution, the experimental total pressure which is measured through experiment, right, or observed total pressure, and the total pressure calculated from Raoul's law. Okay, let me use the word calculated. Calculated total pressure, these two are actually equal in the case of ideal solution. In the case of ideal solution, these two are equal. Therefore, the difference between these two, delta P. What is delta P? Delta P is nothing but observed pressure minus calculated. Okay, right? Total pressure observed minus total pressure calculated. Since these two are equal, the quantities are equal, so I'll get 0. Delta P also 0. Okay, so these are all some useful information for ideal solution. Keep this in mind. Now just go through the options again. Question number 5, which one of the following is incorrect? We have to find out incorrect option. Option A, delta H mixing is 0. Yes, that is correct. Option B, delta U mixing is 0. That is also correct. Delta P, observed pressure, total pressure minus calculated pressure. Yes, these two are equal, so it should be 0. Yes, that is also correct. Delta G mixing is given as 0. Students, observe this carefully. If you mix two liquid and if you form a solution, if the solution is formed, definitely delta G mixing should be negative. Okay, delta G mixing should be negative value, but here it is given 0. So the incorrect option among the 4 is option D. So for question number 4, the correct option is D. Take down. Is this clear, student? Is this clear? For this, you should remember these informations. Is this clear, student? Any doubt here?
Yes.
Yeah.
Yes.
Okay, right. Now let me go to the next question. Question number 5. Right. Just go through the question. Which of the following statements about the composition of the vapor over an ideal 1:1 molar mixture of benzene and toluene is correct? I repeat, which of the following statements about the composition of the vapor over an ideal 1:1 molar mixture of benzene and toluene is correct? Assume that the temperature is 25 degrees Celsius. Given vapor pressure data at 25 degrees Celsius, for benzene it is 12.8 kilopascal and for toluene it is 3.85 kilopascal. Okay, we need to find out the correct option from this. Options are given. Vapor will contain equal amounts of benzene and toluene. Not enough information is given. Vapor will contain a mixture, a higher percentage of benzene. Vapor will contain a higher percentage of toluene, which is correct. Yeah. This is also an easy problem here. Yeah. See, 1:1 mixture is given. Okay. That means the solution, I'll take a closed container. You have a solution. That solution contain benzene and toluene. This is question number 5. Benzene and toluene, and both are present in equal number of moles. Okay, we have taken 1 mole of benzene, 1 mole of benzene. Assume like that. 1 mole, 1 mole. So we have 1:1 molar mixture of benzene and toluene. Okay. Now the question is, in the vapor, which composition will be higher? A, benzene or toluene? Whether composition of benzene is higher or composition of toluene is higher? How to find out? You know very well. Here it is given clearly that which are the following statement about the composition of see, it's an ideal solution, right? See the second line carefully. It is given clearly ideal solution, right? Ideal solution. In ideal solution, you know very well, partial pressure, right? Partial pressure of benzene. Let me write benzene like this. Benzene. Okay. Partial pressure of benzene is equal to, according to Raoul's law, it is equal to mole fraction of benzene, right, into total pressure. Into total pressure. Mole fraction of benzene into total pressure. Okay. Then for toluene, partial pressure of toluene is equal to mole fraction of toluene into total pressure. Right, this is according to Raoul's law. Total pressures are equal. Total pressures are equal. Right? And Okay. Actually I made a mistake, I'm sorry. This is according to Dalton's law. This is according to Dalton's law. This is according to Dalton's law, where these mole fractions are mole fractions in the vapor state. Okay, but we have to relate with the liquid state. So let me write for Raoul's law. Students, observe carefully. The previous two equations are applicable for Dalton's. This is for Dalton's law. In Dalton's law, these mole fractions are mole fractions in the vapor phase, but we have to compare mole fractions in the liquid phase. For this you must use Raoul's law. According to Raoul's law, partial vapor pressure of benzene is equal to mole fraction of benzene in the liquid phase into vapor pressure of pure benzene. Vapor pressure of pure benzene. Okay, then partial pressure of toluene is equal to mole fraction of toluene into vapor pressure of pure toluene. Pure toluene. This is the formula. Okay. Now go through the option. The vapor will contain equal amounts of benzene and toluene. Not enough information is given. Vapor will contain higher percentage of benzene. Vapor will contain higher percentage of toluene. Okay. Yes, how to find out. See, here we have taken equal moles, right? Equal moles. Therefore, mole fraction of benzene and mole fraction of toluene are one and the same here. Mole fraction of benzene and mole fraction of toluene are same, right? So this is, and this one are same values. Therefore, the partial pressure depends on the pure vapor pressures. The one having higher pure vapor pressure will give higher partial pressure in the vapor state. Students, observe this carefully. Observe this carefully. Since the mole fractions are same, the partial pressures depends on the pure vapor pressure. Okay. Now you see the pure vapor pressures of benzene and toluene. For benzene it is 12.8 kilopascal. See the question? 12.8 kilopascal. For toluene it is 3.85. Right? Since benzene has higher value of pure vapor pressure, so the partial pressure of benzene in the vapor should be more. Okay, so here it is given vapor pressure of pure benzene is greater than the vapor pressure of pure toluene. Since this is greater, this partial pressure will be more. Therefore, the vapor will contain higher percentage of benzene compared to toluene in this solution. If it is an ideal solution, yes, you can say. Is this clear, student? Any doubt here?
No, sir.
Right? Yeah. Take two. Okay. Now, the next question number 6. At 100 degrees Celsius, question number 6, what is given? At 100 degrees Celsius, vapor pressure of a solution of 6.5 gram of solute in 100 gram of water is 732 mm. Okay, right. If Kb value is 0.52, the boiling point of this solution will be okay. 4 options are given, right? Let me write first. Solution contains 6.5 gram of solute. So mass of solute is given 6.5 gram. As I told you, 2 represent solute, 1 represent solvent. W2 means mass of solute. W1 means mass of solvent. What's the mass of solvent? 100 gram of water. Here solvent is water. Okay, keep that in mind. Solvent is water. Right? Which gives a pressure. Vapor pressure of solution is given. Vapor pressure of solution is 732 mm at 100 degrees Celsius. At 100 degrees Celsius, vapor pressure of solution is given. This is vapor pressure of solution. Then Kb value is given. Kb value is 0.52. The question is the boiling point of the solution will be, okay, you know very well delta Tb equal to Kb into molality. I am not using I here because here it is given simply solute. Okay, students, observe carefully. Whenever the solute is not mentioned, whether it is electrolyte or non-electrolyte, you have to consider the solute as non-electrolyte. Okay, for non-electrolyte I is equal to 1, so I am not using that. Okay, and what is delta Tb? Delta Tb is nothing but boiling point of the solution minus boiling point of pure solvent into Kb into m. Okay, so we need to find out this T. So T is equal to T naught plus Kb value is given. Kb value is given. I am going to use that. What is molality? Molality is nothing but number of moles of solute divided by mass of solvent in kilogram, but I am going to use in gram. If you put in gram, 1000 should come in the denominator, that I am bringing it to the numerator into 1000. Students, observe carefully. It's a very simple one, but you have to do it carefully. W1 is available. What is W1? Yes, weight of solvent is given 100 grams. Kb value is given 0.52. T naught is the boiling point of pure water. Okay, because solvent is water. Boiling point of pure water, you know, it is 100 degrees Celsius, right? Or I can write 373 Kelvin also. Okay, 100 degree Celsius, right? Since we are going to take only the difference here, okay, if this is in Celsius, you will get the solution also in Celsius, right? It's a very simple one. Now, the quantity that we don't know is N2. What is N2? That we don't know. That's why the vapor pressure information is given here. So what I'm going to do first is I'm going to calculate this N2 using the vapor pressure information. Students, keep this in mind. This is very important. For pure water at 100 degrees Celsius, okay, the vapor pressure of pure water is 760 mm, 1 atmosphere, 760 mm. Okay, now what I'm going to do, you know very well from Raoul's law, P naught minus P by P naught, vapor pressure of pure water minus vapor pressure of solution by P naught, relative lowering of vapor pressure, which is equal to N2 by N1 in the case of dilute solution. For dilute solution, this we know. Okay, what is P naught? P naught is 760. What is P? P is 732 by 760 equal to number of moles of solute that we don't know, let it be N2. Number of moles of solvent. Listen, mass of solvent is 100 gram. 100 gram. Mass by molar mass of solvent. Here solvent is water. Solvent is given. So if I divide mass by molar mass, I will get number of moles. But for solute, the solute is not mentioned here. Solute mass is available. I have the mass, but I don't know what is the name of the solute. If I know the name, I can find the molar mass, I can calculate number of moles. But the solute is not mentioned. Therefore, you have to calculate number of moles through this one. Okay, so 760 minus 32 is 28. 28 by 760. I'll bring this quantity here. 100 by 18 equal to N2, number of moles of solute. Now, if I simplify this, I'll get the value of N2. Then we should put that value here. This value is 0. Roughly it is 0.20. It comes around 0.2046 moles. 0.2046 moles. Now what I'm going to do, I'm going to substitute this value here. Students, observe carefully how we are proceeding this problem. See, the actual question is calculate the boiling point of the solution. If you want to calculate boiling point, you require N2. To find number of moles of solute, mass is available. Molar mass is not known because the solute is not mentioned. So you cannot find N2 directly. So to find N2, we have to use this technique because vapor pressures are given. Okay, so now what is T? Therefore T equal to T naught is 100 degree. For the boiling point of pure water is 100 degree plus Kb value is given 0.52 into number of moles of solute is 0.2046 into 1000 divided by weight of solvent, which is given under gram. Okay, so two zeros you can cancel. If you multiply this by 10 and if you multiply these and if you add with this 100, okay, you will get the final answer. Let me give the final answer directly. This is 100. If you calculate this value, you will get the value around 1.06. So if I add them, I will get 101.06 degrees Celsius. Okay, students, is this clear? Students, is this clear? Any doubt? You just multiply and check it if you want. Okay, just multiply 0.52 and 0.2046 and into 10, you will get the value as 1.06. Okay, then add this value with the 100, you will get this answer. Is it clear, students?
Yes, sir.
Right, yeah. So this is problem number 6. Now let me go to the next problem, problem number 7. So for question number 6, the correct option, it is 101.06. Yeah, it is closely, it is 101. So the correct option is C here. For question number 6, the correct option is C. Right, no doubt. Now let me go to question number 7. Yeah, what is the mole fraction of solute in 1 molal aqueous solution? Solute is not mentioned, but it is given aqueous solution. Okay, yes, how to proceed this type of problem? This is again a very simple problem, students. They are asking mole fraction of solute. That is, they are asking X2, mole fraction of solute. And what is given? 1 molal solution is given. Okay, 1 molal. Molal. Small m indicate molal. 1 molal aqueous solution is given. Aqueous solution. Aqueous solution means solvent is water. Solvent is water here. Okay. What is meant by 1 molal aqueous solution? You know very well. 1 molal means 1 mole. 1 molal means 1 mole of solute present in 1000 gram of solvent. Correct? That's the meaning. Or 1 kilogram of solvent. 1 molal solution means 1 mole of solute present in 1000 gram of solvent. That we know. Okay. So what is the mole fraction of solute? You know very well, mole fraction of solute is nothing but number of moles of solute divided by total number of moles, that is number of moles of solvent plus number of moles of solute. Okay, so how many moles of solute we have? Yes, we have 1 mole of solute, so 1 divided by number of moles of solute is 1. For solvent we have 1000 gram of solvent, 1000. Since the solvent is water, the molecular weight of water, molecular weight of water is 18. So I am going to divide this 1000 by 18. 1000 by 18 will give you number of moles of solvent here. Students, is this clear? One second, some problem had occurred.
Your screen is stuck.
One second, yeah, that's what I'm checking. Is this clear now, students?
Yes, sir.
Right. Okay. So the number of moles of solute is 1 mole here. See, 1 mole of solute. So 1 in the place of N2 you put again 1 mole of solute. For solvent, N1 is number of moles of solvent. Mass of solvent is 1000 gram. So we need to find out the number of moles of solvent. Mass by molar mass will give you number of moles. Since the solvent is water here, molar mass is 18. So 1000 by 18 will give you number of moles of solvent. And remember, 1000 by 18 is 55.55. Students, remember this value. You need not calculate. For water, 1000 gram of water is equal to 55.55 moles of water. So this is equal to 1 over 56.55. If I add these two, I'll get 56.55. Okay, and 56.55, 1 by 56.55 is roughly equal to 0.017 something, or it will come roughly 2, 0.02, roughly 0.02. Okay, take 2. So the correct option 0.02, yeah, see the option C. In option C, if you round off this, you'll get 0.02. Okay, so for question number 7, the correct option is option C. Is this clear, student? Any doubt here? Any doubt?
No, sir.
No, sir.
Yeah, yes, take 2. Then let me go to the next question. We'll finish off question number 8, then I stop. We'll continue the remaining questions in the next class. Yes, what about question number 8? Question number 8. Just go through the question. Boiling point of 0.2 mole per kg, molality is given. 0.2 mole per kg. Okay, I'll read again. Boiling point of 0.2 mole per kg solution of X in water. X is some solute. Okay, X in water is greater than equimolal. Equimolal means same molality. Equimolal solution of Y in water. See what is given? Boiling point of X in water. Okay, X in water is greater than boiling point of Y in water. Y in water, and the two solutions are equimolal solution. The two solutions are equimolal. Equimolal means molalities are same. Molalities are same. Okay. Which one of the following, see the third line, which one of the following statement is true in this case? Molar mass of X is less than Y. Okay, some informations are given. Students, observe this carefully. Since boiling point is given, you know very well delta TB is equal to I into KB into M. You know very well. I into KB into M. Okay. And delta TB is nothing but boiling point of solution minus boiling point of pure solvent equal to I into KB into M. Right. Now for X in water, boiling point of X is equal to, I can write this as T naught, boiling point of pure water, plus I into KB into molality. Molality is given 0.2 mole. I'll write that value. Similarly, boiling point of Y in water is T naught plus I into KB into 0.2. For both the cases, the solvent is water. Okay, here also water, here also water. For both cases, solvent is water. Therefore, KB also same. Right? KB also same. And the T naught also same. See, T naught is same. Point molalities are same. KB values are also same. Okay, so now if for Tx to be greater than Ty, for Tx to be greater than Ty, I must be greater for X compared to Y. For I to be greater, that means X should undergo more dissociation compared to Y. Students, observe this carefully. For Tx, boiling point of x in water, for Tx to be greater than Ty, okay, for Tx to be greater than Ty, right, the Vanta factor for x should be greater than Vanta factor for y. It should be greater. Okay, Vanta factor, listen, Vanta factor greater than y means x should undergo more dissociation compared to y. X should undergo more dissociation compared to y. Okay, now I'll go through the options. Molecular mass of x is less than molecular mass of y. Okay, that is one information. Then we'll go to the second option. Y is undergoing dissociation in water while x undergoes no change. Actually, x should undergo more dissociation. Okay, so option B is wrong. Option C, x is undergoing dissociation in water. Yeah, that is correct. Then what about D? Molecular mass of x is greater than the molecular mass of y. You know very well, if Vanta factor, right, if Vanta factor is high means x should undergo more dissociation. So x should undergo dissociation. That's the meaning. X is undergoing dissociation. If x undergo dissociation, Vanta factor will be more. If Vanta factor is more, boiling point will be more. Okay. Y, assume that y does not undergo dissociation. Y does not undergo dissociation. Let us assume like that. Undergo dissociation. Okay. So based on this, you can easily answer. Right? Take down. Is this clear, student? For Tx to be, because our T naught, everything are equal. So for Tx to be greater than Ty, I for x should be greater than I for y. I is nothing but Vanta factor. Okay, I greater means that component should undergo more dissociation, or it should undergo dissociation. Okay, students, is this clear? Any doubt?
Yes, sir.
Okay, right. I stop here. We'll continue the remaining questions in the next class.